trusses. They are an age-old technology employed by engineers for centuries to help bridge gaps, both literal and figurative. This particular bridge here is a very beautiful and important bridge to the University of Maryland campus. As you can see, it helps guide students across the Paint Branch stream, and probably most importantly, it helps unite the School of Engineering campus to Looney's Pub, a popular Friday hotspot, and really a hotspot every day of the week. Joking aside, trusses are very important technologies that are utilized in both small and grand applications.
For those of you that are from Maryland, you might recognize the Hayden Bridge in Havre de Grace, Maryland. Sorry if I pronounced that totally wrong. And you might also recognize the Francis Scott Key Bridge in Baltimore, Maryland. Both of these are systems built with trusses. If you look around the world, you'll also see many other famous truss structures, such as the Sydney Harbour Bridge in Australia, and on the west coast in California, the Golden Gate Bridge. At first glance, you might think that the Golden Gate Bridge is actually a suspension bridge, which you're correct, but if you look down at the bottom, you'll see that the bottom of the bridge actually is built with truss structures. Similarly, the Eiffel Tower in Paris, France, one of the world's most famous and recognizable structures, is also built with many truss systems. Trusses not only exist around the world, but they also exist in your house. For example, the trusses that hold up your roof obviously are called roof trusses, and there's also trusses beneath your feet as well, known as floor trusses, which help carry and distribute the load of people walking around. Had you been on campus this semester, you would have worked in a team to build trusses for ENES 102. Unfortunately, that's not the case, but I'll show you some former examples. The one right here you can see is none other than the trusty crab. You've got here the 3 Trusketeers, and probably the most glitterified truss of all time, Trustin Bieber. Very good times. To provide an overview of today's lecture, first we'll do a brief introduction to trusses. Then we'll talk about how we're going to analyze trusses. And by that I mean we'll first discuss how to draw free body diagrams for them, kind of figure out what's going on inside. We'll discuss a methodology called method of joints, which is a way to solve for the different forces in each member of the truss. And last but not least, we'll talk about something called zero force members, which is a useful tool in helping you solve trusses a little bit faster. So let's briefly first start off by talking about an introduction to trusses. So given that trusses are used in all these different applications, and there are many different types of trusses that you can choose from, we have to ask ourselves, why do we use trusses at all? To better understand why we use trusses, we'll first look at how we can analyze trusses and see what's going on inside to see why they're beneficial. One of the main reasons that we use trusses is because they're very good at redirecting and redistributing forces. Consider this bridge here, which is built out of a simple beam that this car would drive on. As the car would drive into the middle of the beam, you would notice that the beam would begin to sag. What you could tell is that the top piece of the beam would be getting squished as it bends inward, meaning that it's in compression, whereas the bottom of the beam would actually be getting longer and would be stretching out because it is in tension. Trusses act very much in the same way, in that they'll take an applied force and distribute it throughout the truss system into compressive and tensile forces. Let's consider this very basic truss right here, which is essentially just a triangle labeled A, B, C. On the bottom left you see a circle, which represents a roller support, and on the bottom right you see a triangle, which represents a pin support. This very basic truss here you can see is comprised of 3 different truss members. Those members are member AB, member BC, and member AC. Now, as we've talked about in the past, you can assume that all members of a truss are pinned at both sides, meaning they have a pin at A and a pin at B, and usually in a truss no forces are applied except at the point where truss members meet. Essentially what this means is that all of the members of a truss are going to be referred to as what's called two-force members. And the 2 forces that every member of a truss will carry are, you guessed it, tension or compression. Let's consider the following example. Imagine that you and 2 other friends got in the formation shown on the left. If the 2 people in the top, numbers 1 and 2, were holding a board, and someone were to apply downward force shown in blue, and the person down at the bottom, 3, is holding the feet of persons 1 and 2, what would each person have to do to keep everything stationary? Well, you can imagine that if you were person 1 or 2, the blue force is pushing down. Therefore, what you have to do is push up to prevent that from happening. But because you're standing on a frictionless floor, you would notice that you would begin to slide either to the left if you're person 1 or to the right if you're person 2. Therefore, the goal of person 3 is to pull inward, the arrow shown in green. Effectively, what this means is that the people at the top are being compressed. They feel like they're getting squished, whereas the person on the bottom, because they're pulling inward, they feel the people being pulled out. And because they're pulling in, they feel as though they're getting stretched. Now let's go back to our truss. If we replace the 3 people in the previous example with members AB, BC, and members AC, you'll see that very much the same thing is happening in the truss as was happening with the 3 people. Members AB and BC, to prevent themselves from being pushed down, have to provide a force up. But you can see because the members A and C are attached down here to this pin and roller, what effectively is happening is that as they push up here with their hands, they also have to push down on the floor. This means that these 2 members are in compression. The member at the bottom, member AC, is trying to keep the truss together as well and has to pull inwards, both at point A and at point C. This is why we say that member AC is in tension. This is a perfect segue into discussing and introducing our first methodology to solve trusses, which we will refer to as the method of joints, which you can see right here. The way the method of joints works is it essentially asks you to draw a free body diagram of every single joint, or the place where members meet inside of a truss. In this particular case, we are looking at joint A, which was the bottom left corner of our truss. At that corner, we had 3 things going on. We had member AB, which we discussed was in compression, member AC, which was in tension, and the roller support, AY, which we draw down here as well. Remember that a roller is a support that can only ever push up. So we draw that force as going up right here. Now, the reason we draw the forces the way that we do in terms of member AB and AC is as follows. For a member that's in compression, essentially what is happening at the joint is that the joint is pushing inward, which you can see here shown in these blue arrows. So because these members here feel as though the world is coming in on them, what those members have to do is they have to apply an outward force, or a force that goes into the joint to prevent them from being squished. Members that are in tension, however, feel the exact opposite. They feel as though the forces from the joints are actually pulling away from them. And to prevent those things from being pulled away, members that are in tension pull inward to fight that being stretched. That's why in our free body diagram, members that are in tension are drawn with an arrow facing away from the joint, and arrows or members that are in compression have a force that goes into the joint. One is fighting being squished, members in compression, and one is fighting being stretched, which is members in tension. Now we'll look at the example that we were talking about a minute ago, our simple truss ABC, and we'll use method of joints to solve for the forces inside members AB, BC, and AC. Here's how this works. Looking at our truss, much like in the past, we can choose to draw a free body diagram of, in theory, all 3 joints, but in this case we only need to draw 2 joints. So just like in the past, you always want to try and avoid the pins, because a pin, as we remember, has 2 reaction forces, both a reaction force in the X, CX, and a reaction force in the Y, CY, whereas our force over here inside of our roller is only going to be up, AY. So what we probably want to do first is draw a free body diagram of point B, which is at the top of our truss. If we draw that free body diagram, which I'll do right here, we can see that we've got point B, which we'll label with the letter B. We draw our 100 Newton force going down, and then we draw the 2 forces of the members, AB and BC. Now we know that these 2 members right here are both in compression, so we draw them pointing inward toward the joint B. And we label them both with the forces AB and BC. Now, In order for this to be a complete free body diagram, we need to also include the angles that we know, which in this case are 60 degrees and 30 degrees for angle AB and BC respectively. So, looking at this as our free body diagram, we can now write our sum of the forces in both the x and the y direction to solve. Because something you can realize is that we've got one known force, the 100 newtons, and then two unknowns, which is member AB and member BC. So if we sum the forces in the x direction, and we set that equal to 0, this will lead us to the equation that ABX, which is the AB, times the cosine of 60 degrees, going to the right, minus BC times the cosine of its angle, 30 degrees. From this equation here, we can simplify and solve in terms of AB in terms of BC or BC in terms of AB, whichever we choose. If we do that, what we would find is that AB would be equal to BC times the cosine of 30 divided by the cosine of 60. This leads us to the following relationship, which tells us that AB is equal to 1.7332 times BC. So this tells us that AB is actually taking more of the force than member BC. Now what we can do is we can sum up the forces in the y direction for this joint B. When we do that, we get the following. We get the y component of member AB, which will be AB times the sine of 60 degrees, plus the y component of member BC, which is going to be BC times the sine of 30 degrees, minus the 100 newtons, which is acting downward. By plugging in from above, what we can do is put this entire equation here in terms of AB, or BC. So when we plug 1.7332 BC in for AB, down in this equation right here, what we come up with is the following equation. We get 1.732 times BC times the sine of 60 plus BC times the sine of 30 minus 100 equals 0. This essentially, if we replace all of the signs and with their particular number, we would find the following equation. We would get 1.5 BC plus 0.5 BC equals to 100. So looking at this equation here, it's fairly straightforward to realize that 2 BC is equal to 100. Therefore, BC will be equal to 50 newtons. And given that we had drawn the arrow facing inward this way, this means that our force in both of these members, given that we have a positive answer, at least for BC, means that this is a member that is in compression, which is the direction which we guessed in the beginning. We now box our answer, and we're good. What we now do is we plug BC into our earlier equation right here for AB, and we determine that AB is equal to 86.6 newtons, which again is also in compression, which instead of writing the word out, we'll draw a letter C and put that in parentheses to indicate that that member there is in compression. What we just did was we solved for the forces in members AB and BC. Now what we need to do is solve for the force in member AC, which is the last and final member of the truss we have yet to analyze. Now, as I described earlier, the way that we want to do this is we will want to look at joint A, because joint A contains a roller, and it will make our analysis easier to solve as we will have one less reaction force to worry about. So the way that we'll do this is we'll draw a free body diagram of point A. When we draw the free body diagram of point A, we draw joint A, obviously. We then also label the force of the roller, AY. And we draw the forces of the two members that we know, We've got member AB, which is compression, which we draw as facing inward towards the member, and we draw member AC, which is in tension facing out from the member. Because we already know member AB from our previous step, we only need to write one equation of equilibrium here. In that particular case, we only have to worry about the sum of the forces in the x direction, which we set equal to 0. This leads us to the equation that AB, as we know the angle here is 60 degrees, times the cosine of 60 degrees, so essentially the x component of AB, which is actually going left, so we set this equal to negative, plus AC, which is going to the right and is purely in the x direction, and we say that this is equal to 0. Given the fact that AB is 86.6 newtons from before, we can plug that into our equation right here, and we solve for AC and determine that AC is equal to 43.3 newtons. Now, because we drew AC coming out of the joint A, that defines that this member is in tension. Therefore, our 43.3 newtons, the fact that it's positive, means our arrow was drawn the correct way and means that AC is in tension, which we will indicate by drawing parentheses T and boxing our final answer. And there you have it. That's how you solve for all the forces in the members of this truss using method of joints. So in our last example, you just saw how we solve for this truss here, A, B, C. We solve for the forces inside each member of the truss. The answers we got were the following: that AB is equal to 86.6 newtons in compression, member BC is 50 newtons, also in compression, and member AC was 43.3 newtons in tension. One of the main reasons we use trusses is because if you look at all of the forces in each of the three members, AB, BC, and AC, all three of them are less than the force that's being applied, which is 100 newtons. That's really good that everything is less than that. So one of the main reasons that trusses are good is that if you design them well, they can create a system whereby no member takes as much force as actually is applied to the system. So it makes the structure very strong and efficient at carrying external loads. So method of joints not only works for the simple triangle system that we just did a second ago, but it also works for more sophisticated truss systems like the one shown here. Instead of being just truss ABC, this truss here has three triangles and is effectively referred to as truss A, B, C, D, and E, which has three external forces, F1, F2, and F3. To apply method of joints to this truss here, it's no different than what we just did. You'd have to draw a free body diagram of every single joint in the truss. Now looking at this, you would see you'd have a free body diagram for joint A, B, C, D, and E, and you would replace every single member of the truss with its equivalent force. Now something you can notice in this particular free body diagram is that every force is being directed out of the joint. Before, we had drawn them either in tension or compression because we knew which one was going to be which, because it was a very simple truss. In a truss that's more sophisticated like this one, it's good convention to always draw every arrow for every member going out from the joint that you're drawing it. This essentially is making the assumption that every force is in tension. We'll find out later that that's not the case, but it's good practice to keep things consistent. Now, in this particular example, the way you would solve it is you would look at the joint with the fewest number of forces to solve, or places where you knew things. In this particular case, you would always need to make sure that you have no more than two unknowns at any given joint because you have two equations that you can use to solve, the sum of the forces in the x and the sum of the forces in the y. Given that each joint allows us to write two equations, the sum of the forces in the x and the sum of the forces in the y, this tells us that we can write 2J equations for the number of joints that there are in the truss. Effectively, what this tells us is that the number of unknowns has to be equal to at least the number of joints times 2 for the truss to be solvable, which you can see is the case for this truss right here. That truss is good. The truss on the far right is statically indeterminate, or meaning that we cannot solve no matter what we do, because in this particular truss we have 4 joints, meaning we have 8 equations that we can write. However, because we have 6 members and 3 reaction forces, this tells us that 9 is going to be greater than the number of equations that we can write. So the fact that we have 9 unknowns, whereas we can only write 8 equations, means that this is unsolvable. Now here's a simple thought exercise for you here. Using what we've just gone through over the last couple slides, I want you to think about the following example, where again we have another simple truss, ABC. Consider the possibility of, would it be better to have theta 1 and theta 2 be small, let's say approximately 0 degrees, or would it be better to have theta 1 and theta 2 be large? What effect would this have on the structure? By better, I essentially mean which truss would be more efficient at carrying the load? One where the thetas are small, or one where the thetas are large? I'll give you a minute to think on this. All right, have you come up with an answer? Let's look at how this turns out. If we were to make both angles equal at theta equals 45, what you would see is that the forces for members AB, BC, and AC, which I've solved using in a simple Excel spreadsheet, effectively using the method of joints, you would see that the forces in members AB and BC are equal, and that the force in AC is less. Here you can see that if the applied load were 100 newtons, then the output force in every single member is less than that. That's great news. What would happen if we made the angles really large? Well, because the force is being applied down, if we make the angles very large, that tends to make AB and BC more vertical. And as we do that, it becomes more effective for those members to essentially prevent the truss from collapsing. So you can see that the force in AB and BC are now actually less than they were in the previous example. 50 is less than 70, and member AC is effectively carrying no force at all. What would happen now if we make the angles very small? If we make the angles very small, what you can see happens is that to fight the downward force, our members have to provide massive forces to be able to fight that. And you can see that our truss would be very inefficient. So effectively, for a truss, you want to use angles that tend to be larger in the direction at which the force is applied, so as to make sure that the truss is efficient. Now what we're going to talk about is something that's called zero force members. And as I was explaining before, effectively when you solve trusses, you'll want to be able to solve for zero force members so as to be able to make your problem solving much simpler. Now to introduce the concept of zero force members, let's think about everybody's favorite part of school, group projects. Now how many of you have ever felt like this guy right up here? Well, I'm sure you've probably all felt like this guy, where you are doing pretty much all of the work and you are just the absolute all-star. Dun, 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 dun. Whereas the other people in your group pretty much do nothing and don't really contribute to the project in any meaningful way. Well, guess what? This is exactly the same thing that Trusses experience. They also have lazy group members. And that's my dog barking. So if zero force members are members of a truss that don't do anything, why would you even bother having them in there in the first place? Well, consider this stupid example shown below. Imagine a table with 5 legs, one in the middle, which is a little bit off of the ground. You can imagine if you put a very, very heavy box M1, what might happen is that the top of the table might bow and actually begin to look like a happy face. In the event that the top of the table bows, you can imagine that the third leg would actually move down and begin to touch the ground, in which case this member would actually be doing something meaningful. So the whole point of using zero force members in a truss is that maybe at some initial point they don't carry any load, but eventually they provide greater structural stability to the truss in the case that different types of loads are put into the truss than maybe you initially expected. So how do we compute what members are zero force? Well, the way that we do this is we just use method of inspection. We follow a couple different rules to identify zero force members, and we do this by using effectively method of joints. Now, rule number 1 tells us that if 3 members meet in an unloaded joint, of which 2 are in a direct line with one another, then the third member must be a zero force member. Now that sounds like a bunch of jibbledy-jab, but here's what it really means. Essentially, if you look down here, and we've got 2 members, this member and this member, these members are in the exact same direction. They're purely only in the x direction, whereas the member right here is pointed in the y direction. If we did a sum of the forces at that joint, you would realize that no matter what the vertical member did, it could never cancel out or be included in the sum of the forces in the x direction. Therefore, that particular member is 0. In the similar case over here, these 2 members are again collinear. They're in the same exact line, and they both have only x components, whereas this member right here has both an y component and an x component. Because that has both components and its y component cannot be canceled out by anything else, that member must also be a zero force member. Another type of joint where we can determine that the members are zero force members is at an unloaded joint where 2 members meet in different directions. So again, what you can see is that this member right here has purely x direction forces, whereas this member down below has both an x direction force and a y direction force. Because there is a y direction force in this member, that cannot be equaled out by any force in the top member. Therefore, both of these must be 0. And the last condition or rule to identify zero force members is that if 2 members meet in a loaded joint and the line of action of the load coincides with one of the members, then the other member must be a zero force member. Now again, that all sounds like a bunch of jargon, but let's look at how this plays out. If we look right here, this is our applied load in green down at the bottom. Our applied load is meeting these 2 members here, which look very similar to this condition right here. Instead of them being unloaded, they are loaded by this force right here in purple. Because this force in purple is actually in the same exact direction as this member right here, we can tell that this and this are both going to be pretty much equal to each other. Whereas this member down over here has components that cannot be equaled out by these 2 forces over there. Therefore, that member is a zero force member. And really, this particular case right here is actually pretty much the same exact case, if you look more closely, as this case here. Whereas instead of it being an unloaded joint with 3 members, it's a loaded joint with 2 members. And in our example, kind of over here, you can see that this would be a member, and you could almost treat this as a member right here. And because these 2 members right here would be in the same line, the third member would be 0. Now, if all of that was very confusing, I totally understand. Let's think about this in simpler terms. Let's assume that you are playing a game of tag with 3 people. And the 2 people at the bottom who are trying to catch the person at the top can only run in the x direction, whereas the person on the top can only run vertically up and down. Now, if you played this game of tag in an intelligent way, and you were the top person, no matter how much the people on the bottom run, they can never get onto the same plane as our person above. Therefore, there's nothing they can do to ever catch our racer. Therefore, this game of tag is pointless, and the person at the top shouldn't even play because they can never be caught or can never catch the people below. Now let's look at an example where we'll try to identify the zero force members in this truss using the rules that we just described in the previous slide. Essentially, this truss here has lots of stuff going on. We've got a pin at A and a roller at point O on the far right. We've got two applied forces as well acting on this truss, which are load P acting right here and load Q acting right here. What you should do is utilize the rules shown at the bottom to identify what members, if any, in this truss are zero force members by inspection. I'll give you a minute or so to think about it. Alright, the video is about to move on, and if you're not done yet looking through the entire truss, I would pause it for a minute and try and think a little bit longer before you move on. Now what you can see here is the solution to the previous question, which was asking you to identify the zero force members of this truss via inspection. Now let's figure out if you were right and why or why not. Well, using the three rules down below for our zero force member, what we'd effectively want to do is we'd want to look at every single joint in this truss and try and identify any place where one of these three examples is true. If we look at joint A, we can see that we've got two members, member AB and member AC. However, because we have a pin right here, that's going to have a reaction force in the X and Y. Therefore, we cannot say that members AB or AC are zero force members. So we'll get rid of that right there. And we'll move on to a different joint. Now let's look at joint B. If we look at joint B, we would see that we've got member A, B going this way, and we see that we'd have member BD going this way. Something you can recognize is that these two members are collinear, and member BC is going a totally different direction, which is this way. Now if you look, that's exactly like this particular example right here, where member BC is the vertical member and the other two members are the horizontal members. The member BC, because it's going in a different direction, must be a zero force member. So we highlight that in pink. Now, what's interesting about zero force members is that once you identify a zero force member, like BC, you should remove that from the picture and reanalyze everything again. So what we'll do is we'll scratch out BC and we'll look around. So again, A, nothing changes. If we look at B, well, we have AB and BD, so nothing changes. Both of those could still be members with force in them. But now what we would do is we would go to member C. And if we go to member C, what we would begin to observe is that we would have member AC has a force this way, and member CE has a force this way, whereas member CD has a force going this way. Well, if you look at this, this is actually the exact same example as the one over here, where we've got two collinear members on the bottom and an angled member at the top. That's exactly why member CD is a zero force member. Therefore, that member gets canceled out and is a zero force member. We would repeat this process throughout the truss, and we would pretty much realize that the other members that are zero force are the ones that are in pink, which are JI, IL, LM, and NM. Now, to answer one question you might have, which is why, if we look at force F, or joint F, is FG not a zero force member? We can see again that we've got FH and FD going this way, whereas FG is going a totally different direction. Shouldn't that be the case that we just showed below more or less a minute ago? The reason why FG is not a zero force member is because we have an applied load right here, acting down at this joint. That changes everything. Because we have an applied load, member FG cannot automatically be assumed to be a zero force member. So Much like before, because this truss is symmetrical, we can say that member JI is much like member BC, and M is much like BC as well. And because both of those are gone, we would repeat the process of the way in which we found that member CD was a zero force member, and we would cross out both IL and LM. Now we'll look at another example where you can practice identifying zero force members. Consider the following truss shown here, with a roller at joint H down over here, and a pin over here at joint L. What you should do is identify any zero force members in this truss, again using the 3 rules of inspection that we have up here. I'll give you a minute or so to look through this and try and identify which members are zero force members. Alright, if you're still thinking about it, I would pause the video here and give yourself a moment before you move on to the next slide where I'll show the solutions. Ta-da! Here we go. Here are the solutions to the previous question I asked you to find the zero force members in the truss. Again, I'll just show you 1 or 2 of these, and I think the practice will become pretty clear after you've kind of looked at it a little bit more closely. If we go to member H, for example, or joint H, I'm sorry. If we look at joint H, we can see that we've got 3 things going on. A reaction force going this way, the member force in HD going this way, and the member force in HI going this way. So given that we have those 3 things right there, nothing is a zero force member because none of it meets the conditions that we've shown. The next place we would probably want to go and look is at joint D. Now if we go to joint D, what we can notice is that we've got member HD with the force this way, member DA with the force this way, and member DI with the force in this direction here. This particular case is exactly like this case right here, up on the top right corner of our page, and because of the relationship of AD and DH being collinear, we can determine that DI is a zero force member and should therefore be eliminated from our truss. So let's do that. Remember, once we eliminate DI from our truss, we have to assume that that is not there and reanalyze every single aspect of our truss. So the next place we would probably go to would be the exact opposite side of our truss, joint G. If we look, joint G is the exact same and is symmetrical to joint D on the other side. So given that it's symmetrical, joint GK is also a zero force member. And we can see pretty clearly that if we look at joint E, joint F, and joint Z, all 3 of these are again meeting this condition right here, which is that we've got a T. And because we've got a T, that essentially means that these 3 members are also zero force members. We would cross all 3 of them off. Now here's where you can see the domino effect of zero force members come into play. If we've gotten rid of member DI and member EI, right here and right here, then that would actually leave us with 1 member right here, which is member AI. If we look at member AI and that joint right there, we would see 3 things. We would see IJ going this way, we'd see IH going this way, and we would see member AI going vertically upward. Well, that would look exactly like the condition that we just described before, which is our T again becomes evident. As a result, because of the domino effect of zero force members, member AI is also a zero force member, and last but not least, for the same reason, member KC is also a zero force member. So there you have it. That's how you solve for all the lazy members of your truss. And it's all done via inspection and understanding that because the sum of the forces in the X and the sum of the forces in the Y must both be equal to 0 at every single joint, there are some members that cannot be satisfied with those 2 equations. And that is the case, Those are referred to as zero force members. Thank you for watching, and that concludes our lecture for today. If you've got any other questions, there's a good resource down below which allows you to learn a little bit more about trusses. And in the following slides, you'll find more resources as well. What we'll talk about next time in our next lecture is going to be something that's called method of sections. Now, this is another type of solution methodology that you can use to solve trusses. And really, the difference is that it's going to be very similar to like what we've been doing for internal forces. And that instead of looking at every single joint of a truss, we'll look at a section cut, where we'll either choose to look to the left and solve for that piece of the truss, or we'll choose to look to the right and solve for the members on the other side of the truss. This will be very useful because it'll allow us to look at our truss as a single structure, where instead of looking at only single pieces, now we won't see anything unless it's cut through. So the three things that would be visible if we made a cut here would be member CE, member BE, and member BD. What this will allow us to do is potentially solve the truss much faster than by using method of joints. And we'll discuss this in a lot more detail in our next lecture.
Hey everyone, check it out! Not only are trusses really cool structures, they're also really awesome playgrounds. Sometimes when I need a break from work, I come out to the truss on campus and practice all sorts of really fun acrobatics. Whoa! Whew! That was close. But don't worry, you can trust me when I say I've never once fallen off of the truss before. It's really fun. Whoa, God!